All right, good morning, everybody. Welcome to another installment of Autodesk Virtual Academy as presented by KETIV Technologies. The date is September 16th, 2021. Where did the summer go? I'm not really sure, but I am quite looking forward to the fall time already. The weather's nice and cool here in Southern California, and my electricity bill couldn't be happier. And so we got a really interesting topic here for you guys today, more of an interesting presentation, really. So I'll explain a bit about that as we get into it, but we're going to be talking about Nastran and simulation in general here today. Joining me here today is going to be Pedro Chow, our simulation practice lead here at KETIV. Pedro, are you on, my man?
I'm here.
There we go. All right. Yeah, how's the bathroom construction going, man?
You can hear. Yeah, everything was quiet, and I think they knew that I was presenting here and decided to make noise. I apologize for that.
It's no problem. Yeah, I'm glad we could have you. Yeah, Pedro's actually relatively new at the company over here, and he's kind of shoring up some of our simulation practice here at KETIV Technologies. And so he is quite a get, and I'm very appreciative of your time here today, Pedro. So thanks again for being on here. And Pedro's going to be supporting me throughout this conversation as we get more into the kind of simulation conversation. Do you have anything else you want to say here, Pedro, right at the outgate here?
Well, I'm just going to mute myself whenever I'm not speaking here, but yeah.
Much appreciated. Yeah. And so again, this is a traditional Zoom webinar. So if you guys haven't been on a webinar, there's going to be slightly different controls than the regular webinars that you may have been on so far. There's a Q&A section, there's a chat panel. We'll be submitting information as we go along, but feel free to submit questions as we go along as well, or any concerns if you have issues with quality or audio, for example, and we could make adjustments live as we need to. And also be on the lookout for a survey at the end of the session, as we do take feedback pretty seriously, and we're always looking for ways to improve this weekly webinar. Okay. And so that said, let's get right into it. Let's see what we got going on here today, shall we? And I'm hoping you guys could all see my screen here so far. We are looking at the agenda here today, right? Agenda, we're gonna do some quick introductions. I do wanna talk a bit about Pedro. I wanna talk a bit about KETIV's simulation practice here that we've been putting out recently. I want to talk a bit about simulation overall. And as you notice from the title, we're actually going to be doing a rerun of our Nastran 101 session from a couple of years ago now, actually. So Nastran is, of course, one of the different solvers that we have available, but we're going to be talking about it as a part of our overall simulation practice solution here at KETIV. And of course, quick summary at the end and a Q&A at the end as well. And again, feel free to submit questions throughout the session if you have any concerns or questions along the way. Okay, cool. Let's see what's next over here. Pedro, you want to talk a little bit about yourself, man? You got quite a lot of history on this page, huh?
A little bit, yes. So I'm the simulation practice lead here at KETIV. I joined the company about 2 months ago, and I have over 30 years of experience doing simulation. Primarily on the mechanical side. I have worked in many interesting projects. I worked, just in case you are wondering what is Spanish or Portuguese name doing before a Chinese last name. I grew up in Brazil, and so that's where I got my naval engineering education. And but I have worked in the Brazilian space program. I have worked in the Brazilian nuclear program. I worked in some, secret projects when back in Brazil, where we were doing some uranium enrichment project. And
are you allowed to tell us that? Do we have to cut the stream here? Oh my God.
It's not a secret anymore. But it was interesting that that project, I had to sign saying I couldn't discuss what I was doing with anybody. So that was very interesting. But, I have worked also in the Atomic Energy of Canada, which is a nuclear program in Canada, designing and analyzing CANDU nuclear reactors, 300 megawatts, 600 megawatts. Did seismic analysis on a research reactor as well. And all of that was done using ANSYS, which is one of the products that we have here at KETIV.
Yeah. I'm always surprised at like the breadth that, ANSYS really covers, because that's a lot of different stuff in a lot of different places. You don't necessarily expect to see simulation per se, at least not structural simulation, right?
Right. So, as a consequence, Adam asked me to put a fun fact about myself. So I have lived in 3 different continents, born in Taiwan, grew up in Brazil, and then North America.
Wow.
And 4 different countries. So at home, it's truly a United Nations. We have people born in 3 different countries: Taiwan, 2 of my daughters born in Canada, and then a younger daughter born here in California.
Oh my gosh. Wow. Yeah. Pedro's such an interesting individual, man. And just for some perspective, you guys are wondering, I mean, Pedro's been doing simulation longer than I've been alive for. So he's been at it for quite a while. So again, I appreciate all the expertise you bring to the company and to this country.
Thank you for calling me old, Adam.
Of course, you're welcome. And so again, if you guys have any questions about simulation in general, feel free to submit them during this one, because I'm sure that regardless of the industry that you're in, there's probably some application that would be relevant to you guys here. So let's get into it. Let's see what else we got over here. So yeah, a big question we've been asking ourselves and our customers, Pedro, is when and why do we simulate over here? Can you tell us a little bit about what's going on the slide here?
Yeah, sure. So this is very interesting because we saw this picture at the ANSYS side. So the A that you see there is the logo for ANSYS. And simulation is almost like it gives you a superpower. So when you talk about doing tests, right? Tests can tell you that if your component passed or it didn't pass, right? But you don't really know why it passed or why it didn't pass, right? And then I think that's where simulation will bring you a lot of value. You can, for example, if you're doing a structural analysis, you can understand exactly what is the load path that in your component, and then it can tell you how much load is going to this part of the component, how much load is going to the other part of the component, and you can really dissect what is happening in the model or in the component you're trying to design or analyze. When I started doing simulation over 30 years ago, I think because of computing power limitation, there was only so much you could do. I can still remember doing plotting a relatively small, it's a small model for today's standards, but back then it was a relatively large model. I think we were analyzing the wheels of a train, and just half model, and something like 1,400 elements. I would issue a eplot command. I could go out for lunch, come back, and then it was just finishing the eplot, plotting the elements on my screen. So that's when it was in the beginnings of the finite element. Today, compared to what we used to do 30 years ago, we can do a lot. It's almost limitless. So simulation is in telecommunications, 5G, 6G, Internet of Things, autonomous vehicles, AI, healthcare. The list is shown there, but basically almost anything you can think of, you can apply a simulation to it. Not only stress analysis, that's where I come from, but batteries, electric aircraft, anything that you can think of, you can use a simulation for. Okay, so simulation allows you to really speed up the product development. You can think that you need to build a prototype. It'll take days, weeks, months to just build a prototype. If you're talking about analysis and simulation, we would like to say you can do that in a couple of hours, but realistically speaking, depending on the changes you are incorporating into your model, it may take some time. But the power is there. Once you have built a baseline model for simulation, with a relatively little effort, you can just go make all the modifications, on the computer virtually, and then just run, and then at that point it's just a runtime in your computer. So you can go through a lot of iterations, a lot of different what if scenarios a lot faster than if you would have to go through a physical prototype. Okay, so here at KETIV today, presentation is going to focus on Nastran. And by the way, Nastran stands for NASA Structural Analysis. So it was developed within NASA during the space program when John JFK, he made that famous speech saying, we are going to put a man in the moon by the end of this decade. And inventor Nastran is based off that original Nastran program that was developed at NASA. And then we also have ANSYS available here at the KETIV. But as a solution provider, as a services provider, we want to be a software agnostic. So whatever our customer is using for simulation, we want to be able to deliver in that platform. Okay. So you can go to the next slide if you want, Adam.
I got you. Yeah.
And so KETIV is a technology provider, but we are much more than that. We want to be. We are a complete, engineering services and technology provider. We have a lot of experience in-house doing all sorts of simulation, going from stress analysis to computational fluid dynamics to electromagnetic analysis. Okay, so what we want to do is we want to help our customers to be to improve your product, to understand how your product is going to behave in real world. Okay, and then we want to do that in a very cost-effective way. So what we'll do is we want to partner with you, we want to sit down with you, understand your simulation challenges, understand your product development challenges, and bring that process virtually, create a model that can really mirror the reality for you. And we want to truly work with you to make you successful. Here you can see some contact point here, the KETIV. Jim Ochoa is our director for the ANSYS business. And if you want more information, if you want to work with us, please do contact him. You have his email address, you have his phone number here, and we're here to help you.
Yeah, absolutely. Yeah, and so again, the practice, the new kind of simulation services we have at KETIV are kind of a great way to get those capabilities without necessarily taking on the effort and cost yourself, right? And so definitely keep that in mind as we go over all of this. And I just pasted Jim's info in the chat message there as well. So if you guys want to have more conversation about any of this stuff, especially partnering with us for any kind of services, feel free to reach out and expand your capabilities with us, no problem. But that said, let's go ahead and get into the meat of this. There's a few more slides at the end of this presentation as well, but the main topic of today's presentation is going to be Nastran in particular. So we originally aired this video about, I want to say like 3 years ago or something like that, quite a while ago now. However, part of the effort at KETIV recently is just to kind of gauge interest in simulation again, right? Kind of understand where the interest is. I want to see if Nastran is still interesting to the audience, for example. And so this particular session is a very entry-level kind of discussion about Nastran 101 and the use of elements inside of Nastran itself. So video's not terribly long, but it is going to be a rerun. So feel free to, watch, of course, and the original video is available online in addition to all of this. However, Pedro has expertise in both ANSYS and Nastran. So if you guys have any questions about Nastran, especially its general applications, feel free to message us. We want to make sure the conversation is still engaging as we go ahead and run this video again, okay? And so that said, yeah, let's get into it. Yeah, if that's all right with y'all. Do you have any thoughts on, I guess, Nastran, just right out the gate here, Pedro? I'm going to start the share here off screen, if you don't mind.
Yeah, as I mentioned, so Nastran started, at NASA. It is probably one of the standards when it comes to, dynamic analysis. It's very widely used in the aerospace industry. And then, we can talk more about ANSYS, I think, when you want to move on to multi-physics and type of simulation. Then Nastran has some limitations there. But, the good thing is that, there are a lot of solutions for you available within the KETIV portfolio.
Perfect. Okay. And so let me know if you guys could hear this video. This was a relatively new workflow, so let me know if you guys could
shorten the testing phase. It allows you to explore design options early in the design cycle.
Let me know in chat if you guys can hear
before
audio
expensive
so far.
prototypes are created and tested. Now, in order to create and calculate and compute displacements and stresses and strains, or any other results that may be of interest, the FEA process, the finite element analysis process, can be used to obtain these desired results. So the process begins by breaking down your CAD model into small building blocks, into a series of finite elements. And these, as you can see here, are the elements. Now Nastran In-CAD is going to take this CAD geometry for you, and it can create a mesh. A mesh is just an interlocking of these elements, a mesh for you. Now, these elements are connected to each other at points called nodes. And it is at these nodes that the loads and constraints of any kind, whether they be structural or thermal, it's at these nodes that they get applied. Now, why is there such a big focus on elements in mesh? Why is the type of mesh and the size of mesh important? Now, this little plot shows the effect of the mesh on the von Mises stress at an area of stress concentration. Now, mesh number 3 has considerably more elements than mesh number 1. And as we can see, the change in the value in the actual final result is sizable, because especially between mesh 1, when you look from mesh 1 to mesh 3, it's almost double. And this is because the number of points that are present to, 1, represent the geometry, and 2, to calculate these results at these points of stress concentration, these areas of stress concentration, has greatly increased from mesh 1 to mesh 3. Now, in general, as a general rule of thumb, a higher element count is going to lead to greater solution accuracy. In most problems, however, refining the mesh beyond a certain point leads to very small, if any, changes in solution. This convergence is one of the primary means of actually verifying the results of an FEA study, and we'll look at that in short. You can control the mesh to lead to convergence by reducing the element size, and in conjunction, monitoring the changes in the results. Now, models with certain complex elements tend to converge with smaller element count than others, but the time and resources associated with these complex problems may sometimes be prohibitive. So most FEA studies, at the end of the day, require you, the analyst, to strike a fine balance between analysis time, the cost to run the analysis, and the desired accuracy. Now, let's look at the different types of finite elements that we have in Nastran and CAD. Now, the simplest element is a line made of 2 nodes. It's called a 1D element. There are 3 types of line elements supported by Nastran and CAD. bars, beams, and pipes. And you can also have an axial preload on these elements. Now, to define the geometry or cross-section for a beam element is going to require several properties, several cross-sectional properties. Now, to input this data, you can either put that in from empirical data, or what's recommended is that you use the inbuilt element library, which has a lot of preset standard sizes that you can just pick, and it's going to populate every property that you need for you. 2D elements are typically surface elements with triangle or quadrilateral shapes as their basic shapes anyway. These surface elements can have either regular shapes or irregular shapes in the model itself. And they're often used for 2D elasticity problems, since they account for plane stresses and plane strains. Now, the fundamental property of a shell element is the actual thickness. You can assign this thickness property to geometric surfaces or geometric solids, depending on what your model requires. Now, 3D elements or solid elements are usually used to mesh volumes. Most 3D solid elements only account for translational displacements, and this is something to keep in mind. So the choice of element is very important. When using solid elements, the geometry is entirely described by the geometry of the CAD model. Now, Nastran In-CAD has tetrahedral elements, uses tetrahedral elements, and there are two types of those, linear and parabolic. Linear tetrahedrons are mathematically stiff. So it's best to use these only for trend studies where the absolute results are not nearly as important as the relative changes in the results. Parabolic elements are much more suitable and much better general purpose elements that can be used for most applications. Now, Nastran In-CAD terms the mesh itself as an idealization. So essentially, this comes from the fact that we're idealizing the geometry to look like these preset standard elements. Now, for those of you that may have used the software, we can set up different kinds of elements, different materials, doing completely different things, performing differently in the same model. And you just have to create a different idealization for each type. Right? So for a complex model, for example, it can have solid elements. It could have an area that requires shell elements, and it could have components that require beam elements. So you can use all of these in conjunction, and the idea is to be able to convert the 3D CAD model into the best possible finite element mesh. Let's jump into the actual program real quick. And so this is a simple railing, really simple analysis. Now, this was created using inventive frame generators. So this comes in, these beam idealizations are automatically created for us. But if we did want to create a new one, you go into idealizations, select your type of elements. So for this, we're going to use line elements. So you can select bar, beam, pipe, let's say bar for this one, select a material. And if your material doesn't show up here, you can always add it to the list. Oops, there we go. You can always add it to the list by selecting a material here. So for this one, if we consider, let's say beam 1, and we see that this structure is represented by a bar element, and the reason we're using a bar element instead of beam element is that we're not subjecting this to actual bending. So beam elements are allowed to bend, bar elements typically are not. Now for this particularly, since this was used, this was created using frame generator, the properties come in from Inventor. So all your cross-sectional properties are already in here. But if you didn't have that, if you didn't have those properties to begin with, then you can select cross-section, and you have different kinds of dimensions, different shapes that you can use, different channels. So you will have to put in these properties. So I do have an analysis set up already. Right, so I just want to make those visible. Now, our mesh settings here, we're going to use an absolute mesh size of 1. We're going to use parabolic elements because, as we discussed, these are good general purpose elements. Now, I can also go into the settings, mess with the tolerances on here. So let's just say I use a tolerance of 0.01. I can generate mesh, and we'll see those different colors. So if I just hid my actual model, this is our mesh of bars and beam elements. And the colors here represent the colors, or they correlate with the colors in your idealizations. So the mesh is quite fine. Loads are applied on the nodes, constraints as well. So that's all we need. We can also add one more load if we like. That's going to be gravitational force. So Fy of minus 386.4. Right, so this here shows you that gravity is acting as well. So we're good to run now. Nastran In-CAD also is really, really quick at solving problems. Now these, notice how your results are in terms of bar stresses, not necessarily in terms of 1 Mises stresses, solid 1 Mises stresses, but this actually behaves now as a series of bars and beams. Now the next model that I have is this little channel here. So I'm going to jump into Nastran In-CAD, and if you're new to the program itself, then the way you would get in from Inventor is it's an environment within Inventor. So just go into the Environments tab and open Nastran In-CAD. So I'm going to use a linear static model for this as well. And notice we don't have an idealization here. So sometimes that can happen. So we want to create one. Right? Now this is a really thin element. It's a really thin component rather. So we want to make sure we use shell elements, and this is when you would use them. When you have a thin walled component that needs a thickness, but you don't necessarily want to be modeling that as a solid. So I can select associated geometry and select different components of the geometry in case I want different elements. But if I don't select this, then these settings are going to be applied to everything, to the complete geometry. So I want to use a thickness of 0.125 inches. And this is just going to be a standard thickness. Okay. Oops, hang on. Notice I didn't select the material here, so I'm just going to pick something simple, alloy steel. Right, so there we go. So our material populates here, and we can we can now select that from the drop-down menu. Now we're going in to actually set this up. So it's going to be fairly simple. I'm going to be selecting edges, fix those two holes there. I also want to apply constraints on this end as well. I want to constrain the motion of these edges and make sure that the only way it's constrained is that it cannot translate in the y direction. I'm also going to apply loads to the same three edges, same side of it. It's going to be enforced motion, actually. So I'm just going to displace this upwards by 0.01 inches. So now we can go ahead and create a standard mesh, a default mesh. And the way you verify whether your mesh is okay or not is you look at these areas of high stress concentration, right? This doesn't look like a particularly good mesh because the elements that we have here don't exactly represent a circle. So instead, we can go into our mesh settings. I'm going to change my element size to something smaller, 0.10 inches, and update that mesh. Okay, that's slightly better now. We have all of our information in, so we should be good to run.
And just keep note too that I know it seems pretty self-explanatory, but the more elements you have, the smaller you make those elements, the longer it's going to take to calculate this. So you could get like infinitesimally small, but your computer might not be a huge fan of that. The cool thing is we're actually running In-CAD right now on some laptops. We're not even running on like super powerful desktops. So just note that even our not super stellar laptops can run simulation like this. So you don't necessarily need a supercomputer anymore to be able to run advanced analysis.
Yeah. So that was even though we had a fairly fine element mesh, that didn't take very long to run. So Nastran is actually really powerful in that sense. You can also solve a bunch of different element types, problem types. So just as with the 1D elements, where our results were all in terms of bar stress and bar 1 MEC stress and bar displacements, here we're looking at the shell itself. So depending on the type of elements you use, the assumptions you make are going to be different, because this is clearly an approximation of the actual physical problem that you're required to solve. So depending on what kind of problem you're solving, what elements you use, the assumptions you make will have to be different, and those assumptions will have to be factored in to your final results as well. Now, one other thing that I did want to show you here is, let me just make these invisible. And one other thing that I wanted to show you was the actual mesh convergence factor. Now, we know this is a good mesh because if you look at the mesh convergence error, the maximum error here is about 0.4%. So that's okay for a solution error. So this is your preliminary way to verify and validate your results from a simulation is you look at the mesh and you see if there's anything you can do to actually improve upon the accuracy of those solutions. The last model that I have for you guys is a solid model. This is really simple. It's just it's a regular beam with a hole through one end of it, the loading end of it. So again, this is already in Nastran In-CAD, and this is how the problem comes into Nastran In-CAD from your CAD software. Especially for solids, typically an idealization gets created automatically.
Cool. We'll just fire up Inventor real quick. While he's doing that, I'll answer a couple of questions. While Nikhil blew up his Inventor. Good job, Nikhil. But let's answer a couple of questions here. Can we import assemblies for analysis? Yes. You can import anything from an Inventor for analysis. Just curious as to what you need to bring in, if it's the whole assembly per se. And then the second one is, does Nastran In-CAD make use of multi-core capability? Nikhil, can you answer that in about 5 seconds while you're hitting the open on this file?
Multi-core capability, yes and no. That's the 5-second answer.
There you go. Okay.
That's going to require much deeper discussion.
Definitely. So Ian, if you definitely want to talk a little bit about that, being able to use multi-core capabilities on your CPUs, definitely reach out to us and we can take care of that. So Nikhil's got this guy open.
Almost.
Awesome. And so Nikhil mentioned earlier that if you open your Inventor and then you hit that Environments tab, and then you hit Nastran In-CAD from there, if you don't have Nastran In-CAD in that list, it could be one of two things. It could be you haven't installed it, in which case you need to install it, or it's not, the add-in is not loaded. And essentially you just go into your add-ins, there's a big list of checkboxes, and then you just make sure you hit the checkbox for Nastran In-CAD, so that gets loaded.
Okay. So thanks for answering those questions, Nigel.
Yep.
So this is how it comes in. I'm able to click it now, so thank goodness for that. But this is how it comes in. A solid idealization gets created automatically. And if you don't have a material already set up in Inventor, then it comes in as generic. So you'll have to go in and change that material.
But if you do have an Inventor, say you assigned 6061 aluminum to that in Inventor, in your modeling environment, it'll bring it over, which is like kind of awesome.
Yeah. So for this, I'm just going to choose a material. I will pick 6061 aluminum because Nigel seems to like that. So, and the color here is just to represent your actual mesh. So this is a really simple problem, just a very simple bending problem. So I want to fix this end, apply a load on this end, let's say minus 5,000. And minus just represents that it's in the negative y direction. And I'm going to generate a mesh. So look at my settings. I think I can reduce the element size a little bit, turn that to 1.5, generate that mesh again. Right. Now, no matter what I do, though, if you look, actually, let's make this more visible. Green. Right, so if you notice, this still doesn't accurately represent the geometry, the actual geometry. The meshes, there seem to be nodes inside this hole, which is not what we want. So when you have areas of stress concentration like this one, you want to, one of the settings that you want to turn on is go into your mesh settings, hit the settings button, and project mid-side nodes. Just check that box, hit OK, and generate the mesh again. And that suddenly looks a lot better now. So I didn't change anything else. But when you have these areas, holes, fillets, you want to make sure, sharp corners, you want to make sure that you turn on project mid-side nodes. Just a quick tip there. So the rest of it looks good. Should be good to run. And so the profile looks exactly like what you would expect. And again, when you look at your final results, all of your results are with respect to an actual volume. So these are all solid stresses and solid strains and solid displacements.
Definitely. Yeah, I know we went over elements today, but something equally as important, if not more important than elements, are the meshes. They're kind of intertwined and related. You know, elements comprise your mesh, so they're kind of intertwined in that sense. I feel like doing a mesh AVA might be super important, because just being able to refine the mesh in a proper way without getting too crazy in terms of like element number, be very valuable. So if anyone thinks that that is super valuable, as much as I do, definitely make note of that in things like the survey and the questions, and we can make sure to prioritize something like that. I know that when I first started doing simulation, I think, what is that, almost like 6 or 7 years ago, I was just like, man, I've got a really awesome computer. Let me just make the mesh size infinitesimally small and run this thing for like 16 hours. And then you get an answer that's maybe like 0.5% better than the one that took you 30 minutes. It's not worth it. Yeah. So definitely something to keep note of. Where to stop refining your mesh. Yep. At what point you kind of hit that barrier of, you've hit that convergence. Yeah. So definitely keep that in mind. Go ahead, Nikhil.
Yep. And now some of these settings in here, right? The mesh settings, they will require much deeper discussion. So what are mid-side nodes, for example? What's the difference between linear and parabolic element orders? That's probably beyond the scope of this particular AVA, but please reach out to us and we can have that discussion.
Yeah, definitely. The mesh table.
The mesh table.
I'm a fan. I'm a big fan of the mesh table.
This is awesome, especially if you have assemblies. The mesh table is awesome because you can edit your meshes and your different kinds of elements and everything inside this one table and keep updating.
Yep, per each different solid. So if you have multi-body, it's like assemblies, it makes it a lot easier.
Yeah,
so
definitely. So we'll jump straight back in here. So just to summarize real quick, elements in mesh affect the accuracy of your FEA solution. They're one of the things that you actually have a lot of control over. So you need to make sure you're choosing right elements, meshing.
All right, good. Hello, everybody. We're back. I'm going to cut it right there. Scope out that summary screen over there. I do want to kind of get into, I just kind of want to get into our closing transition over here and talk about some of the questions we received throughout this presentation as well. Because as you guys know, if you guys have done any kind of simulation so far, meshing is a huge conversation and a huge part of the process. I was talking to a customer recently and they had like a whole dedicated team to just doing the mesh. It was a part of their simulation workflow, but a lot of good questions here in the queue so far. Let's see if we could address any of these for the benefit of everybody over here. Right, so a few things that came up, you know, does Nastran have brick elements, right? We talked about all the different types of brick elements at the beginning of that presentation, right? There's a lot of different applications and implications associated with that. Yes, Nastran does have brick elements. And sorry, Pedro, are you on here as well? Do you want to talk about brick elements at all? You have anything to say about that?
Yeah, I mean, brick elements, Nastran always had brick elements. I think it is just how it is exposed to the user in Inventor. Typically, brick elements requires a lot of editing on the geometry. As you can imagine, a brick element has 6 sides, and typically your solid would have to have 6 sides, or something that you can sweep from one surface to the, and then the opposite side should have the same geometry. So you have to divide your solid in such a way that it can be hex meshable. So in that sense, it requires a lot more work than TET elements. TET elements, there are the linear TET elements and there are the higher order TET elements. The TET 4 elements typically is not a good element because just a formulation on the TET 4 means that the strains within the TET 4 element is constant. So in areas of high stress gradient, it's just not a very accurate element. For load transfer, for load path, TET elements is just as good. Okay, it is very, very accurate. But that's why I think Inventor Nastran, when you automatically mesh a CAD geometry, it will create a higher order element, which is a TET 10, and you would have to turn that off if you wanted to use a linear TET element. So so just a brief discussion on solid elements. Hex elements are good quality elements, but it requires more user intervention, geometry preparation before you can generate the hex mesh. TET elements, TET 10, high order TET 10s are good elements as well, and that's what the Inventor will do if you use auto mesh there.
Yeah, that's really interesting. Yes, I mean, I was aware of like linear elements and then like solid elements, but I mean, I feel like the conversation is a lot deeper than that for sure. So a lot of different options, which I think would be a good topic for a future conversation for sure. And I realize a lot of these concepts transfer from both Nastran and ANSYS, right? And I figure a lot of FEA solvers, is that correct in general?
Yeah. Most of the these FEA solvers today, they have a very rich element libraries.
That's interesting.
Yeah. So and then depending on the application or type of analysis, maybe some elements is recommended over other elements.
Yeah, I got you. Okay. Yeah. And so I think that's super interesting that it's kind of relevant across different solvers and stuff. And so that kind of element library is something that we'll definitely have to talk more about in the future. Specific to Inventor, someone did ask about the section view or like the internal stresses in particular. There is a way to look inside of the models for the Inventor Nastran stuff. I believe it's tied closely with the section view functionality in Inventor already. So I know you could either like take a face or take a plane and just kind of do slices through the model to see what's inside. I don't have that exact data set or the exact workflow ready for you, unfortunately, but I do know section views are a thing in Nastran and Inventor itself, in fact. So yeah, stay tuned for more info on that, or feel free to reach out if you want to start a case with us and we could look at that specifically. I'm not sure if you'll be able to answer this, Pedro. That last example with the C channel, can you get the reactions at the holes specifically? Basically the bolt load in the Y and Z direction?
Yes, that's one of the output requests.
Right. It could go by axis, right? Okay.
Right. So just in the Inventor menu tree, I think it is one of the options for you to look at.
Yeah. On the results, there was a pull down, I believe, for the different directions as well that you could look at. So a lot of the reporting is pretty configurable in that regard as well. I think you said this about automatic meshing, won't use hex elements. Let's see, looking for beam model. I think this is an interesting question that's come up as well, also from Trevor over here. Looking at the beam model and the results, how do you validate the model? Do you compare it with hand calcs or anything else? And in general, I think this is kind of an interesting question for people that already have access to Nastran and simulation, right? When you do a simulation, Pedro, how do you go from the actual results in Nastran file to validating it, saying it's correct, it's right, it's worthy of being passed on to the next bit of analysis? What does that process look like, would you say?
That's what $800 question or $8,000 question.
Yeah, it sounds like a bit of a wall to overcome.
Yeah, I mean, I think we as analysts, we have to do all our due diligence to make sure that results are correct. So typically what you do is that if you have any closed form solution that you can do some simple hand calculation, you start with that just to make sure that the results from a finite element model makes sense, right? You can do convergence studies. I think the video showed some convergence errors there, so that would be one good way of checking the model. Another way that you always want to make sure that the load path in your structure is correct. So there are many things that you can check to make sure that the results that you're getting make sense. And do testing. I think in finite element analysis, it is garbage in, garbage out. Eventually, and all these most companies, what they would do is that in the end they need to do a testing to validate everything. So what you do with a simulation is that you gain confidence in your model, and then you play with a lot of what if scenarios. You come up with a optimized design, and I would say that one day we'll be able to replace a physical testing with an analytical model.
Could only hope, yeah.
But I think everybody wants to see physical testing.
Yeah, exactly. If not just for the analyst, then for everyone else with the team, right?
Right.
Yeah, that's a really interesting point. Yeah, and so I mean, I always kind of imagine analysis as part of a larger workflow, anyways, right? So it's not necessarily the end all be all of your process, but it does let you make informed decisions. It lets you iterate and innovate for a lot cheaper and a lot quicker than you would otherwise, right?
Yeah.
So that's something good to keep in mind for sure. And before I head off to the end over here, I do want to make a point, right? This is obviously a rerun of a previous session, and I think maybe we'd all prefer something live in general. However, it's not always possible, and so I do have a playlist, actually a list of playlists available for viewing as well. You guys should be able to see my screen here. I'm going to post this link in chat as well. And this is our YouTube channel where we host all of these recordings and more. And so if you guys weren't aware, ANSYS and the ANSYS side of the company does their own series of webinars as well weekly for the past 26 sessions over there, as you could see. But we have a variety of videos from AVA ourselves. So if you want to learn more about Nastran, there's a whole dedicated Nastran playlist over here as well with the Autodesk side, and then some other specific stuff and smaller tidbits like these tutorial ones over here. I could recommend any of these playlists and any of these videos if you want to learn any more about simulation on either side of the fence. Okay, so check that out for sure. And we did have one more question over there. Do you have any hand calcs for the C-beam example so you know it's correct? Yeah, I don't. I mean, Pedro might have some explicit documentation on C-beam analysis and stuff, but the closed form solutions for C-beams, I think, are largely solved, right? I'd be surprised if they weren't.
Well, I think for the C-beam, you can go to Rourke, and then from Rourke you can calculate, maximum stresses, but probably not for that specific boundary condition that was shown in the example.
What is Rourke exactly, Pedro? What is that? I'm not familiar.
Rourke, I think it's called the formulas for stress and strain or something like that. So it's just a textbook used in school. Yeah.
I was gonna say, yeah, I did like a coffee cup example a while ago, and I asked one of our other simulation engineers for some help. And he pulled out like a bunch of textbooks. He's like, check it out. There's a bunch of thermal equations over here that you could check out. That's just there to validate, right? And so a lot of that still does connect back to that kind of closed form solution, like you were saying. Yeah, Rourke is a good book for sure. Is the C-beam tutorial that I could look at. Oh yeah, I'm not sure about that, unfortunately, Trevor. As far as I know, yeah, I don't know what the original data set is from. Unfortunately, we don't have access to that that engineer or that data set anymore, unfortunately. But yeah, so there are obviously some formulas available in textbooks, like you're saying. And I think it's a really interesting part of simulation in general. So definitely stay tuned for more of that. But I don't think I have any more info for you there, Trevor. We're coming up on the end of the hour over here. I do want to make this kind of a timely one. We did have the summary slide. Not really any new information over here, but as you guys have seen, simulation addresses a wide variety of real world problems. And so I know we talked to a lot of manufacturers and designers ourselves, but you could imagine the possibilities for a variety of other applications as well. Cost-effective iteration and innovation available. Nastran, like you said, we have some documentation on that, like you just saw. A lot of the concepts transfer over into ANSYS and other solvers as well. Check out that playlist in the chat menu. And of course, if you're interested in expanding or extending your team's capabilities, please reach out to us. Jim Ochoa in particular will be able to help guide you and steer our French relationship with KETIV forward if you guys have any more help, okay? Okay, so let's see. Any other comments or questions or concerns? You got anything else for me, Pedro? Again, appreciate you being on here today, man. Any closing comments here?
No, nice talking to all of you guys. And you know, if you need any help, KETIV is here to help you.
Perfect. Yeah. And then again, there is a survey coming out after this presentation, so feel free to comment and let us know if you have any concerns about our structure or suggestions for formatting changes or future topics. We're happy to hear them, and we're happy to keep sharing more knowledge with you guys. All right. So thanks again, Pedro. Thanks to everyone for being on over here, and we'll talk to you guys again next week. All right, take care, everybody.
Thank you.